Also, a warm welcome from my side. I'm Arne Stoll. As already said, I'm here with Annette Bieniusa from the RPTU. And today I will give you a brief overview over this work, proving what OTP promises, so the GenServer and TLA+. So if TLA+ are now coming up questions into your mind, then I will give you an overview over that in a minute. First of all, a small piece of code here. We just have a process, so one that's spawning. It's pretty simple, straightforward. We send and acknowledge and expect that back, and we're registering this process. Question to you, can you see here any issue? You can also just acknowledge that here might be some defects. I've seen someone acknowledging it. So we have the problem that if we consider two processes, the spawning one, so for us, and R for the registering run, that the registering run totally misses out the spawning process. Just run through, and after that, it's not intended behavior. Of course, you can now say, okay, I'm not writing programs like this. I make it different. But what if our program becomes more complex? So what if we have several clients, several nodes, and a server, so the GenServer in the middle? Who want to manage this shared state. What if now we want to have this guarantee that messages are ordered in a correct way, or we want to ensure that clients act mutually exclusive on this shared state? We don't really know, and that's why it's really hard to get concurrent programs right. So what I want you to think about now is think of the programming as a state graph. Every node in this graph reflects one state of the system. Transitions are then allowed behaviors. If you now do unit testing, you can do that and try to cover the whole state space. Eventually, there will be some edge cases, although they are really unlikely to happen, they still can happen and cause some issues in your program. And that's really a problem. So just by testing, you cannot ensure that you have covered the whole state space. That's why testing alone is not really sufficient. We need formal verification. And one approach how you can do that is starting with your problem, defining a specification. From that, you can derive a formal model. You can do some verification on that formal model and generate code and end up with a valid Erlang program. So that's the goal here. There are some different approaches. You can straight away verify your Erlang program, but we decided to do this in this way. And let's go one step back. I've mentioned TLA+. Who of you heard of TLA+ before? Okay, yeah. Oh, that's quite many. Nice. So it's built for distributed and asynchronous systems, introduced by Lamport. If you look it up in the literature, you will stumble upon this name quite often. You can, as before shown, describe your system as a state graph and then define some properties on it, safety and liveness properties, and you can define actions. And then you have a whole state space. You can some sort of define properties which then are tested on the whole state space. This can be done by some operators here. We have this diamond operator. So eventually, this property is true. Always it's true. And you have also some syntactic sugar like this leads to, or some combinations. On top of that, there's also a language called Bluesky. It builds on top of TLA+, and you can automatically generate TLA+ specification from Bluesky. So that's a quite nice thing. We also leverage here quite much. Don't be overwhelmed. That's the overview of the workflow and the start of this project. I will go over it step by step, show you some aspects. On top, we have the specification and the formal model. From that, we use Erlang+. So Erlang+ was developed by Marian Hilsdorf and Annette Bieniusa. In 2024, you can translate Bluesky programs into Erlang. So they've proven the Raft protocol and translated a valid program in Erlang from Bluesky. We also use typer for type specifications, and we do the code generation, end up with an Erlang program. And we can apply this to the test suite. So there's a test suite part of the standard library, and get a result back. On the left side, you can also see EQC, so you can also define properties on your Erlang program directly. Here on the right side, you can see the verification process. Basically, TLC, so the model checker for TLA+. You can there put some properties in it, and I will now go over parts of each of these 3 parts in a bit more detail, what aspects you have to consider there. First of all, for the specification and formal model, very generally, so you can apply this kind of process setup because to every program you might model in Bluesky. So that's very general here, not specifically made for the GenServer. It's also due to GenServer having a different way of spawning processes, and in Bluesky you have to spawn them statically, so you have to define them and how they interact with each other. That's why. We have a server, of course, so the GenServer, some clients and an orchestrator, since we're not interested really in behavior before and after a stop, and a timer. So in TLA+, since we have a state space, there's no concept of time. So we have to define a timer process which just emits can emit or cannot emit a timeout event. So that's the process setup. And of course, the orchestrator starts and stops the server, the client waits for the orchestrator, and we can do some requests, and timeouts can occur every time or any time. A bit more details about the timeouts. Since there's no concept of time, we just have to consider non-deterministically that a timeout can occur or cannot occur. So it doesn't matter if before a request, the timeout occurs after 10 milliseconds or 100 milliseconds. It just matters since we explore the whole state space, so every possible combination of our system. I'm sorry. So it is only crucial to test that a timeout occurs or not occurs. Regarding the verification, there we dive a bit more deeper into the GenServer. We have to ask ourselves, when even is a GenServer correct? I mean, we can do it on the state alone that is defined by the user, and so there's a lot of user-defined functionality in it, but we want to prove that the GenServer is correct in a more generic way. So that's why more general properties are considered here, not specifically from user-defined callbacks. So we won't look into that, but more general properties. A property from Bluesky here, a bit more prettier printed here, might look as follows. So we will look here at no stay messages. If we want to ensure that, then we could define this as follows. We can say for each server, so if we only have one, then the set of server sets is just cardinality 1, and queues is the mailbox. We can ensure that if we have a mailbox with a message in it, this then leads to the mailbox being empty eventually after some time. But solely the statement cannot be used this way because we have to ensure since every client can terminate the server, we have to also incorporate a second condition. So this can only be ensured if there is no client that requested a termination. So there's some nitpicks. I initially started with the simple structure, just thought, okay, if there's a mailbox and there's a message in it, then after some time it should be empty. And this was violated, and I had to refine it this way. But so you can only ensure no stay messages if there's no request from the client asking for a termination. Okay, you should now quit your stuff. Of course, we've proven more than one property. Here's an overview, liveness, safety, and regarding to whom? To clients and servers, more predominantly, of course, server. And some interesting ones are like, we have seen no stay messages, or that the shared state for how the clients can see it is mutually exclusive. Messages are only processed once. So, I mean, we don't know. Maybe they're processed twice. That there's no duplicate delivery. We have a relative order preservation. So if a client sends several messages, then it's relatively ordered. So 13 were here defined in total and also evaluated. Now regarding the code generation. Since we want to come up with a generation from Pascal to Erlang, there are some things to consider. So I've built upon the existing Erlang Plus, as I told you before, which already covered some things which translate Pascal programs into Erlang. But I had to make some few changes. Some things like we have to mark atoms correctly, so they are then also translated into Erlang. Return values are a bit different in Pascal, so it's a bit more technical, but you cannot just return a value, because in Pascal you have labels, and every label is an atomic step. It's a bit different, but you can come up with a solution like this here for the second point. Also, I've introduced tuples. They were not supported in Pascal, and you can use them like this. It's quite useful. Then you have less code and it's more readable. A header file was generated and due to the test suite. So I then apply the generated Erlang program to the test suite. I have to, of course, have some type annotations, and I automatically generate them from typer. Also, it's a bit more technical. I've introduced annotations. Sometimes, as I've shown you, the process setup, sometimes you don't want to translate a process like the timer into Erlang. So that's why, for example, you can then use this height annotation. Also collapse to, since, as I've also mentioned before, if you have some setup in Pascal, then this might be different from the setup of process spawning, for example, in Erlang. So there you can then use this collapse annotation. So you cannot straight away translate Pascal programs into Erlang. You have to make some changes and find ways to annotate your code that you can generate in the end the GenServer API. But because what you want to end up with is an alternative GenServer implementation which adheres to the API, so that you can then just plug in your newly generated GenServer. So that's the main goal here, and that's why you have to come up with stuff like this. It's not a enclosed program which runs on its own somewhere and you can use it in a specific way. It has to adhere to this API. Yeah. So here we have an overview. So at the top, maybe you're familiar with it. That's the Erlang implementation from the GenServer for a call with 2 arguments. And below you can see the Pascal code. So what I want to show is not in detail how the code works, but so that you can see some similarities. And below you can then see the generated version. So it's a different one from the original one, but it works. So you have here the spin operator, because that's a bit more technical. You have to consider that macros are a bit weird. They're not functions, but they're replaced upon translation. And so you have to tell that this macro is actually should stick there and should be translated into a function, so into a method. So that's also available in Erlang. Yeah. So regarding some verification aspects and some analyzing and performance comparisons. So I've tested this model with TSC, and I've done this for example, for 2 clients, 2 requests, and 3 clients, 2 requests. So that's here what you can see here. And really a huge problem is that if you increase parameters, so increase the number of interacting clients and the number of requests, the model gets quite large. So we have here a steep curve. We start initially with 1,500 threads. Pretty simple. That's done in TSC in less than 10 seconds, all the way up to 1 billion states with 3 clients, 2 requests. So you quickly hit a resource limit there. Of course, if you have unlimited resources, you can there increase the number of clients, the number of requests even more. you have to make sure that your model is bounded, so it cannot be infinite of infinite size. You somehow have to check everything, and yeah, so that's a limit here. Regarding the API, so we can see here the functions that were available in OTP 27 and should also be the same in OTP 28, of course. Most of them were generated, so the most important ones like start links, start monitor, start, so just the normal start without links, monitors or so, and the stop functions, synchronous call functions, but some were not generated yet, since they would even more expand the model, and then we even more would struggle with this state explosion. But like cast, so the asynchronous call, reply, and the broadcasting here. Yeah, so you could sit down and also incorporate those functions in the model in the future. Regarding the test suite, as I've told you before, so I've did the verification, I've did the translation, and of course we want to also make sure that what was generated is so we want to double check that this is also correct. We can see that's the original one. I've tested this, 2 were skipped, and there were 74 test cases due to some, as I've shown you here, being skipped, since they were not implemented, but all of them passed, and almost similar coverage, but really doesn't matter because we just proved for our properties that the GenServer is correct. Yeah. Also, what was done is a performance comparison, because you could argue if you now have a generated version, then yeah, but mine is faster, and why should I use it? And we did some testing, and just one client, one server, and they make repeated requests to the server. They solve a complex task, and we start here initially with 1,000 requests, and then all the way up to 10,000 requests over time. They differ to a factor up of 1.5, so that's quite a nice performance, not too worse, and similar performance. Of course, if you then increase the requests, this performance gets a bit larger, this performance difference. The red one is the original one, and the top one, the generated one. Yeah, so summarizing, we've seen that the correctness of the GenServer by 13 properties in total, the automatically generated, reusable, and valid alternative GenServer implementation, and this unique annotation-based approach as an extension of Erlang+. So we can state that the GenServer is proven to be correct, just as OTP promises. And of course, there might be, this is not solely for the GenServer, but we can extend this to different protocols like GenStatum, GenEvent, or different protocols. Yeah, thanks for your attention.
Thank you, Arne. We might have time for just one question. We are running low there. Here first.
You showed in one slide thanks. So to check, I understood, you showed in one slide the original GenServer call code, and then the +cal code that corresponds to that. Is that translation manual or automatic?
Yeah, that translation is automatically done. That was the main goal. So Erlang+, so Erlang, TLA+, that's why it's named this way, was developed before that. And you can just click a button, and by specifying your +cal program in a certain way, I can also show you that, you then get a translated version in Erlang, which you can then use.
Why do you need the generated code at the end then?
Because it's a nice thing that, just think of it, you have this gap of, you have maybe your model somewhere, you have your implementation, and as you develop, put in new features and so on, they might diverge, and the model is not up to date, or the other way around. And that's a nice thing. You always have a up-to-date code base, so your program is up to date because you always can derive it from your former model. So that's the main advantage here. And if you also make sure that the translation, so that was not verified, if you make sure that this was also verified, you can then also be sure that the translation is 100% correct. And yeah.
Thank you so much, Arne. It was really great. Everyone, just give it a warm applause to Arne here.
Thanks.